What I'm going to talk about today is not altogether unrelated with what Alan just talked about. It has to do with structure prediction and graphical models and how what connection can you establish between the two. So very often someone would come to me and say, I have this problem. Would it be better to use neural nets or graphical models? I say, if you use a neural net, you use a graphical model. A graphical model is kind of a framework in which you can cast a lot of models, including neural nets. Particularly the kind of neural nets you've heard about this week, that have latent variables and that are trained probabilistically and all that stuff. So, DBNs are just a particular type of graphical model. Normal feed-forward neural nets are also graphical models, albeit very, very simplistic ones. In one point of view, in the sense that they basically have only one factor, but they're complicated internally in the sense that their conditional distribution, their computing is very complicated. So there is no opposition between different classes of models like this or different frameworks like this. They're very, the views are complementary. There's just different views of the same things. So that's what I'm going to try to talk about a little bit, and also tell you that there's a lot of work, very successful work around structure prediction that are applied to things like natural language processing, speech recognition, and image recognition, as Alan was explaining earlier. And those are generally not deep. And there is some sort of a belief widespread within the machine learning community that they cannot be deep, but it's not true. They can. Okay, so let's start with, so one idea that I've been really obsessed with for a very, very long time is not just the idea of integrating. So you could think of deep learning as the idea of integrating the training of a classifier and the feature extractor simultaneously. But really what I'm after here, and what I've been after since the early 90s, is integrating not just the feature extractor and the classifier, but also some sort of high-level reasoning, contextual information, taking into account contextual information and things of that type. So if you want to train something like a speech recognizer or an image recognizer that decomposes the image into parts, or a handwriting recognizer, for example, which is what I was interested in at the time, you have to include something like something that locates objects, a segmenter, a recognizer, with a feature extractor integrated to it, and perhaps some sort of contextual post-processing that says, you can't have a face above another one, or you're missing a body somewhere, or if you have a sequence of letters, only a sequence of letters that belong to the language are allowable. Or if you have a sequence of phonemes and you're trying to recognize a particular language, then certain sequences are allowed and others aren't. So there are things, constraints like this that you would like to be able to take into account, and that's what people call structure prediction. Okay, and the idea is to make everything tunable. So one thing you can first remark is that we've talked about deep learning algorithms that basically take vectors or arrays of data as input and plug trainable layers in between, and then you get an answer. But there's no reason why you couldn't use something else, something more complicated than an array of data, say a graph, a valued graph. Okay, so let's say all your knowledge about the world and your internal interpretation of it is not represented as an array of data, but as a graph where each arc is labeled by itself by a value, a vector, a label, an array, an image, whatever. Okay. And this seems a little abstract right now, but I'm going to give you some specific examples of how this works. And this goes back a very long time. And you could have modules here that are parameterized, and instead of transforming an array into another array, they basically transform a graph into another graph. And so we call them graph transformers. And if you put them into networks, you can call that a graph transformer network. This concept goes back to the mid-90s, roughly. And so you have to have two things now within this module. Something that basically computes the piece of data that you're going to attach to the arcs of this graph as a function of the pieces of data that you have on the input graph. And then the other thing you're going to have is ways of transforming graphs into other graphs, and perhaps combining multiple graphs into a single graph. And I'll show you some examples of that too. So as it turns out, there's a whole algebra on graphs. that is formally equivalent or very similar or has the right properties as the linear algebra on vectors and matrices. So there are certain graphs you can interpret as vectors in a space, and certain other graphs you can interpret as matrices, and there are operations between them that you can interpret as vector matrix multiplications. So now back to, before I get to this, I'm going to have to tell you something about energy-based learning, and I kind of alluded to this earlier in an earlier talk, but I'm going to sort of recast this for supervised learning. What I talked about earlier was for unsupervised learning. And so there's the series of methods that people have, that have been extremely popular in machine learning over the last few years: structured perceptron, conditional random fields, and things like latent SVM, etc. And they're all descendant of discriminative learning methods that people invented for speech and handwriting recognition back in the early 90s. Or they are reinventions of them, I should say, in some cases. So if you want a whole history of this, there's a paper I wrote with a few of my students called A Tutorial on Energy-Based Learning that has kind of a lot of the details of this, and I invite you to have a look at this. So there's a whole literature on discriminative training for speech recognition, which really were the first people to use what we now call structured prediction, going back to the late 80s. And there was a whole series of people that tried to kind of mix hidden Markov models and neural nets, and you heard some of that, some allusion to that this morning, to try to train HMMs discriminatively so that you could train a neural net in the loop to do the right thing for speech and handwriting recognition. And the pioneers in this area are people like Léon Bottou, Yoshua Bengio, whom you'll hear about, but you probably talk about other things, Patrick Hafner and Hervé Bourlard. All these people were working on speech recognition and integrating the training of neural nets, sometimes convolutional nets, time-derailed neural nets, and hidden Markov models, or versions of hidden Markov models. And then all these people got together at Bell Labs, except Hervé Bourlard, and together with me, and we came up with this idea, graph transformer network, which is sort of an unnormalized form of HMM, if you want. And you could think of structured prediction, conditional random fields as special cases of this. Maximal Markov nets are a little different. Okay, so what about energy-based learning? So if you're going to train a machine to make a decision, you could think of this as kind of an input-output relationship, right? You have X as the input, Y is the output, and you have some sort of classifier neural net, whatever you want, that just produces Y. But that's actually a fairly weak way of building a system, and the reason is because sometimes there are multiple possible answers for Y. And what you'd like is the system to basically not just tell you the best Y, but tells you, you give it a Y and it tells you how good it is. Okay, so basically what you want is some box, some function here, which we're going to call an energy function. So it's very similar to the potential functions that Alan was talking about earlier. So an energy function, except it's got the reverse sign. You want to make it small instead of big. But we're going to have this energy function. It's going to take X, which are observed variables, and it's going to take Y, which would be variables to be predicted, and it's going to tell you if those two, if the two values that you give it are compatible with each other or not. So it's going to give you a low value for the energy if they are compatible, and a high value if they are incompatible. Okay? And so if you think of this as a classifier, perhaps X is an image and Y is a discrete variable that indicates one of the possible 5 categories in that case. And what you do is you plug the X and then you look for the Y that minimizes this energy. In this case, animal has the lowest energy, human has higher, airplane has higher, car has higher, truck has higher too. Okay, so the inference mechanism consists in doing this. Find the Y that minimizes the energy with respect to Y for a given X. Okay, no learning there yet. Okay, what we're going to do now is we're going to parameterize this energy function in such a way that it has the minima at the right place. But okay, so there's a lot of applications of this, of course, not just for image classification, but for things like, you could cast a lot of the problems that we've been everybody is trying to solve into those terms. And in fact, a graphical model, if you think about it, is nothing more than this. It's you have some sort of function which you can interpret as a negative log likelihood of your data, for example, and you're trying to find the settings of variables to be predicted maximizes the likelihood given the ones that you observe, or it minimizes the negative likelihood given the ones that you observe. Okay, so that encompasses probabilistic graphical models, but also encompasses other models that are not probabilistic, that are just based on energy. Hence the name energy-based models. So, for example, you could think of image segmentation as an energy problem, where you have an image and you have another image, which is the output, and you're looking for the image here that is best compatible with the that sort of labels the components of this as best as possible. And it's usually better to formulate segmentation in those terms than to formulate it directly as a X to Y mapping, because there's usually not a single answer. So it allows you to make this sort of minimization process, allows you to build models that are much more sophisticated, because you can formulate now the idea of compatibility between an output and an output in terms of an energy function. And it's kind of more general to view the inference process as a minimization process rather than an input-output relationship. So obviously for things like handwriting recognition, you're turning an image into a sequence of symbols. For scene parsing, for image denoising, you can kind of formulate all of those problems as energy minimization. So the first thing you can remark, which I made the point before, and other people, I think Alan also mentioned that, you can always turn an energy function into a probability distribution using the Gibbs distribution. So you take e to the minus some positive constant times the energy, and if you normalize it by something that you integrate over a variable, you get a conditional probability of this variable that you integrate over, and you condition over the ones that you don't integrate over. Okay, so here, if I want conditional probability of y given x, if I want to do classification, for example, then I do e to the minus beta e to the yx, which indicates some sort of joint energy, if you want. And if I normalize by the sum over all y of that, then I get something that integrates. I get a bunch of I get a function that is positive and that integrates to 1 over y, because obviously if I integrate that over y, I get the same thing above and below. And so that's a proper conditional distribution of y given x. Okay, but sometimes you can't do this because either you cannot compute this for maybe practical reasons, perhaps it's intractable to compute, or perhaps it's tractable, but it doesn't converge. The E function is such that this integral does not converge. And in that case, what you have is an energy-based model that does not have an equivalent probabilistic model. Okay, so energy-based models are slightly more general than probabilistic models in the sense that there are more energy functions out there that are not whose integral is not integrable. So here's kind of an example of why you would want to use this. Let's say you want to do handwriting recognition. You're going to have a bunch of processes that will have to go on. You're going to have to kind of segment the string into possible segments, and there are many alternatives on how to do this. You're going to have to recognize each of the segments, figure out, and the machine is going to tell us whether it thinks it's a character or not, and then which character it is. And from that, you can generate another graph that will indicate the category of each of the characters and their score, and then you can do a shortest path algorithm in there that will select the path that correspond to a particular interpretation, perhaps. And in the end, it gives you an energy, and the path gives you the path, perhaps the shortest path gives you the best interpretation. You can think of this as an energy minimization over all the possible paths in those graphs, where those paths are kind of latent variables, if you want. Here's another example. Let's say we want to do object detection. Okay, so we have a machine here, and this machine has been trained to basically produce a large number here if it is not seeing a face, and produce a small number if it sees a face. Okay, and then we have a little switch here that's activated by this label that's either 1 for a face, 0 for not a face. And this little switch here is going to either choose whatever comes out of this box or whatever comes out of this wire, which is a constant t, the threshold. Okay, so if I show a face and I ask, should I choose this variable to be 1 or 0 to minimize this energy? In other words, should I choose this value or that value to minimize this energy? In other words, is this value smaller than that one or bigger than that one? So if it's smaller, I put the switch in this position, I get the lowest possible energy, and this indicates that there is a face. Okay, so it's kind of energy minimization formulation of detection, if you want, or classification with a threshold. Now, imagine that I have the same kind of image, but now it's kind of over a large field, and the face could appear anywhere in that field. The only thing I need to put is another kind of switch that is another switch here, which is going to pick which of those guys has the best score for a face. Okay, so the lowest value. Okay, because here, remember, it's energy, so low values are good scores. So, so this guy is going to say, you know, do you have a low score? Do you have a low score? Do you have a low score? Ah, you have a low score. So you're probably looking at a face. So it's going to put a switch here, and then it's going to decide whether it's larger or smaller than the threshold, and that's going to decide whether it's a face. So here, what we're doing is that we're observing this variable, and we're minimizing over two variables. One, which is presumably one that we are being told on the training set. We're being told if an example contains a face or not. We're not being told that on the test set. But there's this other variable z here, which is a latent variable. Nobody ever tells us the correct value of this variable. No one tells us where the face is in the image, even during training. They just tell us there is a face somewhere. Okay? And so this is just a variable that we're going to have to minimize over. And that's called a latent variable. If you were a probabilist, we would actually marginalize over it, and there is a way to do this as well. So there's lots of examples of situations like this when you need to kind of do this kind of inference. Things like the pose parameters of objects, orientation scale, blah, 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 lighting conditions for object recognition, partial speech tagging, where you have to generate a sequence, speech recognition, handwriting, scene parsing, where the segmentation of the image into components has to be properly chosen among many possibilities, perhaps. So there's a lot of those situations where you have to search over possible interpretations and pick the best one. So here is what I was just mentioning. Sometimes we have those two variables, y and z, and we could compute, as I said before, using the Gibbs distribution, we can compute a marginal distribution over y, the joint y and z, given the observation, by just normalizing with respect to y and with respect to z. But generally, we don't care about the value of z, so we'd like to integrate that out. And what we do is we just marginalize this whole thing with respect to z. So we integrate this with respect to z, and that gives us that. And then once this probability distribution is marginalized over z, z disappears from it. So now we just have p of y given x, and it's the integral over z of e to the minus beta e of zyx divided by integral over y and z of the same thing. Okay? And if you think about it, this is nothing more than the Gibbs distribution over a particular funny energy that has this form. Okay? This is exactly the same as that, where we only integrate over z. Okay? And so what I can do is I can define a new energy function of this form. This is like, the physicists actually call this a free energy. Okay? And it takes into account all the energies of all the possible values of z. And you compute the integral of the exponential of all those energies, and then you take the log. Okay? And that's a free energy. And basically, p of y given x is just e to the minus beta, the free energy, divided by the integral over y of e to the minus beta, the free energy. Okay? So if you plug this into that, you see that everything kind of cancels out, and you get this. And the minimization process I was telling you about before, where we minimize over z, is just a special case of this, where beta goes to infinity, essentially. It's a limit of this when beta goes to infinity. Okay, so now how do we train an energy-based model? And that's a little tricky. So what we'd like is, let's say we have our energy function, and what we'd like after training is that when we show it the image of an animal, we want that the energy when y is equal to animal, we want that to be smaller than the energy for y not equal to an animal. Okay? Because that would be a guarantee that when we run the inference algorithm, the y with the lowest energy would be the one for the animal, okay, for this particular x. Okay, so let's imagine we have energies of this type. We show a picture of an animal, and the machine says high energy for human, high energy for animal, high energy for airplane, low energy for car, high energy for truck. So it thinks it's a car. So what we want to do is we want to increase the energy for all the wrong answers and decrease the energy for the animal. And we want to do this by tweaking some parameters of the energy function, so that at the end we get something like this, where animal has lowest energy, and that's the answer that's being picked by the inference algorithm. Okay? How are we going to do that? So we can do a bunch of formal definitions, blah, 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 but basically what it comes down to in the end is that you want to define a loss function which is going to take the energy function as an argument, if you want. Okay, so think of this as, it's more like a functional. and it's going to take our training set, and it's going to compute the average over the training set of a per sample loss function, okay, big L here, that's going to say, which energy are you giving to all possible answers? And by the way, here is the correct answer. So now compute something that will make the energy of the correct answer smaller than the energy of everything else. And then we can add a regularization term if we want. Okay, that only depends on the parameters. Okay, now the next question is, how do we design this L function? Skip ahead. So up to now, we've seen we have to design an architecture, which is basically how do we build this E function, and this could include something very complicated like a whole bunch of convolutional nets or something, or DBN. We pick an inference algorithm, the one that gives us the answer given the input, map or whatever, or it could involve complicated things like variational methods and Markov chain Monte Carlo and blah blah blah. We pick a loss function, and I'll show you in a minute how we do this. And then we pick an optimization methods to minimize this loss function with respect to the parameters of this energy function. So I added a parameter here, which is subject to training. Okay, so now we have to design a loss function. And there's a very simple loss function, which is just the average energy of the correct answer over the training set. Okay, so here is an example, and I showed you those animations in a different context before. I was cheating. I was kind of telling you that this energy function corresponding to an unsupervised learning algorithm. But in fact, they're for supervised learning. This variable is the input, and that variable is the output. But in fact, you could think of this as unsupervised learning, where both y and x are to be predicted from each other. Okay, so what I want is the blue beads, which indicate the relationship between x and y, the mapping between x and y, which in this case is very simple. It's y equals x squared. Okay, so y. So if this is x and this is y, the beads here form a parabola. Okay, because y equals x squared. That's the relationship I want to learn. So what I could do is I could just pull down on the blue beads, and if I pull down the blue beads and I assume that the energy function doesn't change its shape too much, I'm going to have a groove of the energy around those blue beads, and whenever I give a particular value of x, the minimum of the energy is at the corresponding blue beads. Okay? So it'd be something like this, and so that's simply pushing down on the energy of the beads. So basically, my loss function is simply the average over a training sample. So for a single sample, is simply the energy of the training sample, the energy that my model gives to this particular training sample. Okay? And I ignore all the other energies. For simple cases, this works okay. In this particular case, the energy function here is designed in such a way that it has to preserve its shape. And so if I pull down on the blue beads, it will keep its shape, and it will only change the position of that cusp here, and everything works fine. But here's another example. I'm not going to tell you why, but this one happens to be happy to generate a completely flat energy function. And when I pull down on the blue bead, it just goes flat. So that didn't work too well. So what do I have to do now? Well, what I have to do now is the same trick that RBMs have to do, which is I have to explicitly pull up on the energies of the points I don't want. Okay? So so I show an x, and I say I want the energy of the correct y to be low, but I also want the energies of the incorrect y's to be higher. And if I have a loss function that does that, then it will prevent this kind of catastrophe from happening. So here's a way to do this, and it's a complicated way of doing it, but it's a popular way of doing it. And it comes from probability theory. I mean, it comes from just a probabilistic approach. And from maximum likelihood. Okay, so I'm going to go through this quickly to show you that the kind of loss function that people minimize when they train probabilistic models is basically a particular way of pushing down and pulling up on energies of things. Okay, so let's say I have a bunch of training samples, yi, xi. Okay, so I have x1 is an input, y1 is the corresponding label I want to predict, and I have p of those. And I have a parameter w, and my model gives a joint probability to all the y's given all the x and the w. And I'm going to assume the examples are independent, so I'm going to assume this can be decomposed as a product over training samples of p of yi given xi. And it would be nice to find a y that maximizes this product, because that would be doing maximum likelihood learning. Okay? Find a w in such a way that the y's that are correct have the maximum probability given all the x's, and that therefore, the other y's will have lower probability, right? Because it's all normalized. So instead of maximizing this, I'm going to minimize the negative log of this. So I have minus log of the product, blah, blah, blah. the log of a product is the sum of the logs, so I have the sum over training samples of minus log of this, right? Now, if I substitute this by the expression I had for the conditional distribution in the probabilistic interpretation, which is this Gibbs distribution, and I plug this Gibbs distribution into that, I get the log of the numerator minus the log of the denominator, right? So I get this. Sum over training samples of beta energy of the correct answer plus log of sum over y of e to the minus beta the energy of all the answers, and I have to integrate this over all answers or do a discrete sum if the answer is a discrete variable. Now I'm going to divide this by beta because it's more convenient, and what I get is this, and we call this the negative low likelihood loss. In speech recognition they call this maximum mutual information. It really means the same thing, and it's the average over training samples of the energy that my model gives to the correct answer, given the input, plus a contrastive term, which is 1 over beta log sum over all possible y of e to the minus beta the energy for that y, okay? And if you notice that there's a minus sign here, which means that as I increase, to make this whole thing small, I have to increase the energies of all these y's, right? So this is going to minimizing this function, we're going to have the effect of pushing down on the energy of the correct answer and pushing up on the energies of everybody else. In fact, including the correct answer, but it's not pushing the correct answer as hard, and so overall it's still going down. In fact, we can convince ourselves of this by computing the gradient of this with respect to the parameter, okay? So we differentiate this with the parameter, we get the gradient of e with respect to the parameter, and then differentiate that with respect to the parameter, and we get this amazingly simple expression. I'm not going to go through the math, but you can trust me. It would be the sum over all y's, or integral over all y's, of the derivative of the energy for this particular y multiplied by the probability that our model gives to this y. So in other words, the force with which the energy of a particular y is going to be pushed up is going to be larger if our model gives a high probability to it. In other words, it's going to be larger if our model gives it a low energy, okay? So, and if you apply this to this little, quadratic function problem, you get this kind of energy function. This is during training. The beads have low energy, and everything around them has higher energy, and they go to infinity because they're pushed up to infinity by this term. Okay. So when this integral is intractable, you can approximate it using Monte Carlo methods or variational approximations or things like this, or you can do atrocious tricks like contrastive divergence, which is really cool. So by the way, I should mention that I'm doing all of this derivation here in the context of supervised learning, but in the context, if you want to apply this to unsupervised learning, it's exactly the same formulas, except you get rid of all the x's, okay? So just keep the y's. So if you think of unsupervised learning, it's the way of unsupervised learning you want to essentially predict, if you want, the y's. You want to predict the input, and there is no variable that you're observing. It's kind of weird. You think that you would need to remove the y, but in fact, you have to remove the x. If you remove the x from all the formulas I showed you, you get the correct formula for unsupervised learning. Okay, so this is probabilistic training, but that requires computing this integral here, which is not necessarily practical. And also it requires having an integral here that converges, which is not necessarily a good thing. So what about non-probabilistic approaches? So this sort of negative likelihood loss has been used for a long time in the context of hidden Markov models and things like this, going back to the 80s and 90s, and even sort of combined with hidden Markov models and neural nets. Yoshua Benjo did his PhD thesis on this, essentially, in the early 90s. And there was kind of other applications to bioinformatics, handwriting recognition, blah, blah, blah. Okay, so here's another cost function you can use. That's a very simple one, and it's the same one that Alan was talking about. It's the structure perceptron. And the structure perceptron loss is very simple. It's the energy of the correct answer minus the energy of whatever answer your machine wants to produce, okay? So if you think about this minimization, that's exactly the minimization we do during inference, right? We find the E that, or we find the Y that minimizes this energy to do inference. Okay, so this is the energy of the answer that our machine produces. And what we're going to do is minimize the difference between those two energies. So this is the energy of the answer we want. This is the energy of the answer that the machine produces. if the difference is 0, so this guy is necessarily smaller than this guy, right? Because this guy is just one of those guys. So this is necessarily positive or 0. And if it's 0, there's a good chance that, that our machine produces the right answer, because the best way to make this 0 is to make this y the same as this yi, okay? In fact, that's not entirely true because of the collapse problem I was telling you about before. It could be that the energy function here is designed in such a way that it could give the same energy to all the y's, in which case that won't work. Okay, so the perceptron, the structural perceptron is not such a great loss function. It's only good in a special case, which is the case of linear classification, but I'll come back to that. So this idea is pretty old. It goes back to a paper of mine together with Yoshua Benjo, Léon Botou, and Patrick Heffner back in 1998. And Michael Collins kind of reinvented this in the early 2000s. Although Michael was actually at AT&T the same time we were, so you probably heard about it before. So here is the kind of a rundown of the perceptron loss, or the structural perceptron, or the non-structural perceptron, whatever it is. This is the normal perceptron, if you want. In a very simple case, where the energy function is for binary classification, where you can define the energy function as just minus the label, which is +1 or -1 times some sort of discriminative function. And if you define this discriminative function as being linearly parameterized in this form, so W transpose a set of features or whatever you want to call them. So here's your energy function. Then the update formula for the minimizing this using stochastic gradient descent comes down to update W with some constant times the difference between the correct answer minus the answer that your machine produces multiplied by the input features. And that's just a perceptron learning rule. Okay? But there are obvious generalization of this for when E is a more complex function and perhaps has latent variables that you've been minimizing over. Here is a slightly more interesting concept. It's the concept of generalized margin loss. So this is a situation where you want to avoid this situation where the energy function can be completely flat, and you want to make sure that there is at least some difference between the energy of the correct answer and the energy of the incorrect answers. Okay, and the way to do this is to introduce a concept called that I call the most offending incorrect answer. Or you can actually do this in a more general form, but this is kind of a simple way of doing it. And so the most offending incorrect answer is the answer with the lowest energy that happens to be wrong. Okay, so you search for an answer over all the space of all possible answers, but you impose it to be wrong, and your definition of how wrong it is depends on the task, obviously. And so that's, okay, so you think it's a car, but it's actually an animal. So the most offending incorrect answer is car. And then, you give me the same energy for animal and car, and higher energies for everything else. And I know the correct answer is animal. So the most offending incorrect answer is car. It's still slightly higher than animal, but not enough, maybe. Or it's the lowest energy answer that happens to be incorrect. In the continuous case, it's a little more complicated to define, but I'll come back to that in a kind of simple formulation. So in this case, you can come up with a whole bunch of loss functions. The simplest one is just the hinge loss. Basically, you take the difference between the energy of the correct answer and the energy of the most offending incorrect answer. Okay, and obviously you want this to be smaller than that, and so you're going to decide that you want this to be smaller than that by at least m. Okay, so you're going to take those three terms, m plus energy of correct answer minus energy of most offending incorrect answer, and you're going to plug it into a hinge. So that the hinge will want to make this 0, and if it's lower than 0, it doesn't care. It's just 0. Okay? So that will cause this to be smaller than that by at least m. Okay? That's just a hinge loss. It's the same as an SVM. But now it's not an SVM that we plug. It's just an energy function here, which could be, a deep neural net, whatever you want. Doesn't matter what it is. A whole graphical model with deep neural nets in it. Doesn't matter. So the idea of using this kind of hinge type loss for structure prediction goes to Altun et al. And Taskar. You have other forms of this, which basically that we came up with, which is sort of a log loss. So it's kind of a smooth form of this, which is very similar to what people use for logistic regression. In fact, it's the same loss as logistic regression. for the binary classification case. But this is applicable to kind of any situation, really. Okay, so again, this tries to make this smaller than that, but it pushes it it pushes the difference to infinity with an exponentially decaying force. Here is another one. So this guy tries to make the energy of the correct answer as small as possible, closer to 0 as possible, and he tries to push away the other one up to a particular margin. And this is very similar. This is essentially the same energy function that Graham Taylor talked about in the context of the Dr. Lim Siamese net, except here it's not necessarily applied to the Siamese net, it's just applied to a generic energy function where you have labels. But you can think of the application of this to Siamese net as kind of a funny special case. In fact, it's this special case. Okay, so people over the years have come up with all kinds of loss functions which are easily generalizable to this situation where you only have an energy function and you're kind of playing with them. So there's things like LVQ2, that means learning vector quantization, version 2, which people like Léon Bottou and Xavier Drencourt used in 1991 to do discriminative training of speech recognition systems. I'll tell you about this in a minute. And there are others that came out of the speech recognition literature. So I made kind of a list of all those loss functions. But in fact, the most general form, it's not the most general form, but there's a general form would be something like this. So the loss would be the sum over all answers of some function, increasing function, of the difference between the energy of the correct answer and the energy of all the answers. And then you add a cost that takes a pair, the pair of correct answer and whatever answer you plug here. You compute the sum of this over y. There's a lot of those loss functions that you can reduce to this, essentially. Maybe with an appropriate redefinition of E. And so the reason I put this down is because some of them have a non-zero margin and some of them have a zero margin. The zero margin ones are not good because they might lead to a collapse. Okay, so perceptron loss can lead to a collapse. LVQ2 can lead to a collapse unless you're careful. But the other ones are kosher. Right, so the probabilistic approach, the negative likelihood is this one, and this one has the peculiarity that you have to compute this integral, and it's, there are a lot of situations where it's much easier to just compute a most offending incorrect answer than to compute an integral over all possible answers. And so these are situations where you prefer to use one of those non-probabilistic losses, instead of the probabilistic loss. Okay, actually let me skip this. Yeah, I'll talk a little bit about that. So let's say you want to do speech recognition, and this is, neural net archaeology here. We're going back to 1991. So this was work done by Léon Bottou and Xavier Drencourt back in the 90s, and they wanted to do speech recognition, single word speech recognition, using a convolutional net, what's called a time delay neural net, because it applies to kind of a temporal sequence and kind of a time frequency representation of the speech signal. And so what you get out of this TDNN is you could think of as a sequence of feature vectors whose temporal frequency is probably lower than this because you might have subsampling going on in this temporal subsampling going on in this convolutional net. So you get a sequence of feature vectors. And now what you want to do is you want to match the sequence of feature vectors to a bunch of word templates which correspond to each of the words that you might want to recognize. So you have these word templates here which themselves are sequences of feature vectors that you perhaps recorded, okay? And what you're going to do is you're going to match those sequences to these sequences. The problem, of course, is that people speak at different speeds, and so this sequence may be a different length than that sequence. So what you need to do is do what's called dynamic time warping. You need to align the sequence here to that sequence here, and you can do this with a very simple dynamic programming program that finds the shortest path in a very simple graph. And you can think of this as the minimization over a latent variable, which is which kind of warping path you're going to choose in this graph to squeeze and extend this sequence so that the length best matches this, each of these sequences. Okay. I'm not going to explain how you do dynamic time warping, but it's very similar to edit distance. So everyone here who has taken computer science courses probably know what edit distance is. So how many insertion, deletion, blah, blah, blah. Here it's just done in the continuous space, so instead of being symbols, it's just vectors. and you know, they match if the distance is small and blah blah blah. So you can easily find this shortest path. And the cool thing about this is that you can just train this whole thing. You can train it, you show it, and you can train those word templates as well. So let's say we want to do digit recognition. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each digit has a template. And we initialize the template with just whatever comes out of here for a particular speaker, let's say. So we're going to show an utterance here by a speaker. It's going to generate a feature vector. We're going to tell the system, look, this word is the number 2. So take the sequence for number 2 and give you the best shot as to what the mapping between this feature vector and that prototype is. Okay, so it gives us our best shot, which is minimization over this latent variable z. And then what do we do? Then what we do is that we say, well, we want this feature vector to be as close as possible to this target. Okay, so we're going to compute the gradient of the distance between the feature vector here and this sequence with respect to that sequence. And it's very easy to do because we basically have a square distance between vectors at every point, so we just sum them up. We compute the gradient of those distances, and we kind of propagate them here. And then we can backpropagate those errors down to the convolutional net. We're going to train the convolutional net with that gradient, but at the same time, we can also say, well, I might as well move the template closer to whatever it was that my network was producing. So you kind of update this guy so it's closer to whatever this guy produced, you know, through the warping function. But the next thing you want to do is you want to move these other guys away from whatever this feature vector is, because otherwise they will all converge to, say, 0, 0, and you know, a 0 constant sequence, and that won't work. You will have a collapse. Okay, so you have to move the prototype closer to the answer that's correctly produced, and you have to move the other prototypes away from them using one of the loss functions that I described earlier. So you can think of each of those guys as a different y, or maybe the value of the discrete variable that chooses one of them as the y. And you have to plug this into one of the loss functions I was describing before that pushes the energy of the correct answer lower and pushes the energy of the incorrect answers higher. Okay? So that's, in my opinion, the earliest known example of structured prediction that anybody has ever done, 1991. Completely ignored papers. Nobody remembers this paper, except Léon Botou's friends. I'm one of them. Okay, so here is for a slightly more complicated situation. So let's assume now that we have, and this is the connection with graphical models, okay? So now we're going to build an energy model. And this energy model is going to be the sum of a bunch of energy functions, 3 in this case. And each of those energy functions takes a subset of the variables, be they inputs or output variables. So let's say our input is, you know, whatever it is, say an image, and our output is a sequence of symbols. So let's say the input is an image of a handwritten word, for example, and the output should be a sequence of letters that correspond to the transcription of that word into, you know, ASCII or whatever. So what we want is we want to take into account the fact that a particular character can follow only a few other characters. So if this character is a Q, then this character is most likely a U if we're talking about English or French. And if, you know, this character is, you know, an A, then there is a probability distribution or some energy for the next character to be something else. And we're going to encode this into those factors. Those factors are going to tell us how compatible two successive symbols are, okay? And we can have a bunch of those factors that take successive pairs of variables in the output sequence. This is why structured prediction is called structured prediction. We have a prediction of a sequence and we want some structure in it. How do we train something like this? So first of all, there are efficient ways of doing inference in something like this, and there is a whole literature on, you know, how you do efficient inference in graphical models, which I'm not going to go into. And so in the case, this is actually a very trivial type of graphical model that happens to be a chain graph. So here you can use something called dynamic programming to find the optimal answer, and I'll tell you in a minute how you do this. In more complex connections, so you could think of those as variable nodes, and you can think of those as factors, and this is a factor graph representation of graphical model. And the difference with sort of the traditional way of writing this down is that these factors are additive instead of being multiplicative, And good means low energy instead of good being high probability, but other than that, it's the same. So it's kind of a log domain factor graph if you want. So here is an example of a factor graph. Here we have an input variable here coming here, we have an output variable here, and we have latent variables in the middle. In fact, this would be a factor graph that would correspond to a deep belief net, for example. The supervised deep belief net has exactly that kind of structure. Each of those is a layer. This is the input observed variable, and these are kind of the hidden layers, if you want. And you have to infer the value of all the hidden layers and the output. But there are other situations for structural prediction where you can have similar things. So let's assume the x variable is binary, and the z variable, z1 is binary, z2 is binary, y1 is binary, and y2 takes 3 variables, okay, 3 values. So it turns out here, we can just write a graph here that indicates each node or each series of nodes on the vertical axis corresponds to all possible values of the corresponding variable. Okay, so x is binary; it's got 2 variables 0 and 1. Z1 has 2 variables 2 values 0 and 1. Z2 0 and 1. Y1 has 3. I'm sorry, this is y2. Y1 and y2. And we're going to put a bunch of arcs here that link 2 nodes, and the arcs will correspond to the value. The value we're going to put on the arc corresponds to the value that a particular energy term takes when the 2 input variables take the corresponding value. So, for example, let's take this guy, for example, that links Z2 and Y1. Z2 can be equal to 0 and Y1 to 0, in which case we look at this arc, and here we write E of 0, 0, or E2 of 0, 0 here as the value, and here we'll write E2 of 0, 1, etc. And the cool thing about this, because this is a chain graph, to find the minimum energy configuration of this graph, we just do a shortest path algorithm within this graph. Okay, we all know how to do this. It's just dynamic programming. Okay, so the inference here, the minimization of this energy function, is very simple because it just consists in doing dynamic programming. Okay, and if it's a tree, you have to do something akin to belief propagation. If it's a loopy graph, then there is no exact algorithm, but you can kind of do approximate inference using loopy belief propagation or beta free energy approximation, CCCP, which is one of Alan Newell's algorithms, or some variational approximation, some other variational approximation than beta free energy, or belief propagation. So I'm not going to go into that. But there is a whole literature on this. David Mackay's book is really good on this, and it's free. Okay, so there's a particular instantiation of this where the factors happen to be functions of whatever variables come in, and the parameters is just a vector that computes the dot product, and you compute the dot product between this vector and the vector of features that come out of this module. Okay, so it's a very, very particular way of parameterizing those energy functions, in the sense that they are linear in the parameters that you're gonna train. Okay, and then you just sum up the energies. And if you do this, and you use one of the loss functions, so if you use the negative log likelihood loss, this model exactly corresponds to conditional random fields. Okay. If you use the hinge loss, this model exactly corresponds to the Taskar and Altun-Hoffman max margin Markov nets or latent SVM, if you have latent variables in there. And if you use the structural perceptron loss, then this exactly corresponds to Michael Collins' structural perceptron model. Okay, so those models are an instance of energy-based model where the energy terms are linearly parameterized in the parameters, which means they're not deep. Okay, and the advantage of this is that the loss function now is convex with respect to the parameters you're training, and so a lot of people who are scared by non-convex optimization are reassured. Okay, but of course, people like us like to play dangerously. So we like deep models, and in fact, the deep models preceded these shallow models by about 4 years. So this is kind of a bit of a folk history of some of the loss functions people have been using in this context, but I'll let you look at this. So the example I'm going to I'm going to describe. It's for handwriting recognition that goes back to a paper that I wrote with Léon Betoul, Joshua Mejou, and Patrick Hafner in 1998. That was published in Proceedings of the IEEE. This is the reference paper that people cite for convolutional nets, because the first part of this paper is all about convolutional nets. But then the second part is all about this graph transformer network business, structure prediction using negative log likelihood and perceptron loss. And nobody has ever read that because it's too complicated, which is why it's not cited by the other guys. I mean, it is, but maybe not properly. So, okay, so here's how you use this idea of graph transformer network to build a handwriting recognition system, but you could use this for anything. And this is a deep structure prediction model that was built in 1994, 1995. It was deployed commercially to read bank checks in 1996. By 1998, it was reading, or 1999, it was reading roughly between 10 and 20% of all the checks written in the US. So your checks, probably, maybe not yours, maybe your parents' checks, have been read very likely by a system like this. And this was trained with, it used a convolutional net as the elementary recognizer for the characters, and it used this negative likelihood loss structured prediction system to train the whole thing in the loop. Okay, so let me go about describing this. So you take an input image, and you run this through a heuristic segmenter. This is something written by hand, which is going to figure out, what parts of the image are possible segments of characters, possible characters, in fact. Okay. So one possibility, for example, is you cut here and you cut there, and you think that each of these pieces is a different character. Or maybe you cut here, and maybe you think that this piece and that piece are two characters. Or you cut here and you think that this piece and that piece are a character. And you build a graph in such a way that every path in the graph goes once and only once to every piece of ink. Okay? That's called a segmentation graph. And so a particular path in this graph corresponds to a particular segmentation, essentially. And each arc in the graph is labeled by an image. Now you're going to run a convolutional net, or whatever model you prefer, but convolutional nets work well, to tell you what category it thinks this character is. And the categories include the characters between 0 and 9, as well as none of the above. Okay? So you don't want a normalized probability distribution over 0 to 9 here. You want a bunch of numbers, 0 to 9, but you want them to be all small if the system doesn't think it's any character, like this is not a character, this is not a character. Okay? So you run the neural net to it, and we're going to pre-train the neural net on pre-segmented characters, but the cool thing is that we're going to be able to train this neural net in the loop so that it gives us the right answer to not only recognize the sequence, but also to give us the right segmentation, even though we're not going to give it the correct segmentation. Okay? The input is just that, and the output, the desired output is just, we know it's 3, 4, but we don't know where the characters are. Okay? So it's kind of a weak form of supervision, if you want. We don't tell the system where the pieces are. So you run this neural net on each of the pieces, and this guy is going to say, well, most likely it's a 3 with energy 0.1, maybe it's a 5 with energy 2.3. And this guy is going to say, well, this could be 3, but with energy 3.4, because really it's not a good 3. Or it could be a 4 with energy 4.4, really it's not a good 4. This guy is going to say, well, that looks a bit like a 4, but really it's not a good 4. And this looks a bit like a 2, but really a bad 2. This guy says, I'm really sure this is a 1. And this guy says, I'm really sure this is a 4. Here. And so you get all those scores in this graph, and you see this machine as taking a graph as input and producing a graph as output, where each path now in this graph corresponds to a particular interpretation of this input graph of the string, where the sum of the cost on the path corresponds to the score you give to a particular segmentation, and those scores are produced by the recognizer. Okay, and each path is a different interpretation. Then to train the system, you're going to say, well, actually the answer is 3, 4. So pull out of this graph the answers that actually that give 3, 4 as the labeling sequence. So there's one here, that's one path that says 3, 4, and there's one here, 3, 4. But this one has higher energy. And then you say, well, pull out the best path of these two, because that's the only one I really care about. And that's the best answer. So this will correspond to an energy minimization where the latent variable is the path, is the segmentation. Okay, so we found the best segmentation that gives us the lowest energy for the correct answer. Okay, so this is the energy that our systems give to the correct answer. It's the first term in our loss function. Okay, energy that the system gives to the correct answer. We've minimized over the latent variable, which in this case is the segmentation. We've not given the system what the correct segmentation is. Okay, so that's phase one, that compute the first term in a loss function. And then for the phase two, we just let the system, so here this is in the case of structured perceptron loss. Okay, in the second case, we let the system choose whatever path it wants. Okay, and it turns out the lowest energy path is the one that does this, which segments the string into three segments and produces the answer 3, 4, 1. So we think this is a 3, this is a 4, and this is a 1. And that's the best scoring answer the system gives. And it's wrong, of course. How do we train this? Well, we're going to compute the derivative or the gradient of our cost function. And the cost function is going to be the difference between those two terms, where the structured perceptron is the energy of the correct answer, which we get here, minus the energy of whatever answer our machine wants to produce, which is given here. It's the sum of the costs that are on the arcs here, right? Compute the difference between those two, we get 0.1, and that's our loss function. Now what we have to do is compute the derivative or the gradient of this loss function with respect to all the parameters of this neural net. And we can just do this by backprop. So it turns out you can do backpropagation through very complicated structures that are not necessarily simple neural nets, but are things that manipulate graphs. So how do I know? So what is the gradient? So let's say I'm looking at, okay, so what I'm going to do is I'm going to say the numbers in parentheses here, which you probably cannot see, at least not in the back, are the gradients of the loss function with respect to the corresponding cost that I've written in the parentheses right before. Okay, and you can very well see that if I wiggle this number by delta, the cost is going to wiggle by delta because this number enters in the cost functions additively and there's no coefficient. If I wiggle this cost by delta, the loss function is going to wiggle by minus delta. Okay, so what that means is that the derivative of the loss with respect to this variable is +1, and the derivative of the loss with respect to that variable is -1. All right, and you can just do backpropagation. Basically, this is a very simple form of kind of network that's built on the fly. If you want, it'd be different for every input, and it's very simple to do backpropagation through it. So you backpropagate the gradient all through, and then there's a situation here. So what's going to happen is that all the path that is in the correct answer will get +1 as a gradient, and the path, the arcs that are in the incorrect answer will get a -1 as a gradient. But since they all come from the same source here, you have to add them up when you backpropagate the gradients. When you have kind of a y connection going up and the gradients come back, you have to add them up. And what it turns out is that you're going to get a -1 gradient here on whatever arc is present on the right side but not on the left side. So these are incorrect recognition, things that have low score but shouldn't have low score. So those two guys, for example, so those two guys are going to get a -1 gradient because they're incorrect. Whereas this guy, which is the correct one but happens not to be in the correct in the spontaneous answer, we get a +1 gradient. Okay, which means that the output for number 4 for this particular neural net that looks at this particular guy is going to get a +1 gradient. So this one is going to be boosted. I mean, negative gradient is going to be pushed down, which is in energy term is the correct thing to do. And this guy said 4 with a low energy, and that's not good, so it's going to get pushed up. This guy said 1 with a low energy, and that wasn't good. It's going to get pushed up. Okay. Then you backpropagate the gradient through the neural net. You add up all the gradients because all of those neural nets are identical copies of the same neural net, so they all share the same parameters. So you have to add up the contributions of the gradient to update the parameters, and you update their parameters. That looks awfully complicated. This is, 1994 technology. It's not that complicated. This works really well for various kinds of handwriting recognition. So this is a case where we actually directly compared with and without this global training through the loop at the word level, and you get a significant improvement. This was a paper with Yosha Benjo. And there is this sort of algebra and graph, which I'm not going to go into, but just mention that it exists. This is actually drawing on work by Fernando Pereira, the same guy from the CRF, as well as Mary Armori, who is a colleague at NYU. And they've worked out how you can formulate operations on graph as kind of in a formalism that's sort of similar to, it's not linear algebra, it's more like the structure, the algebraic structure for those of you who have a math background is more like a semi-ring. That's the right property for anything you want to do with backprop and things like this. So they don't use it with backpropagation. That was kind of our contribution to this. But they use this to build language models for speech recognition systems. In fact, the Google speech recognition system uses something like this. In fact, not just Google, everybody, because but they came out of the labs. And so that's how we built this check reader. Back in 1994 and 1995, it could read about half of the checks. It would reject about half of them, and it would make about 1% error on the one that it read. And those would be detected by other processes. It was commercially deployed in 1996. And as I said before, by the mid-90s, by the late 90s, it was reading about 10% of all the checks in the US. So that's a big success of structural prediction. Before structural prediction was invented. Okay, I'm going to stop here. Thank you very much.